Still good morning, and welcome to the NCCAT Single Particle Short Course. We're moving on towards learning more about the single particle workflow. Our next speaker is Amedee. He's at the ASRC, one of the buildings just right across the lawn from here, as well as the City College Department of Chemistry and Biochemistry. So what is amazing about what Amedee is really doing is using cryo-EM to study molecular complexes. In his former work and his current work, the main thing is that not only looking at static structure, but trying to uncover mechanism, not only by soaking ligands, but getting different transition states. And all that is done through a lot of processing. And this is the topic we're going to go into today. So, Amedee.
Hi, everyone. All right, so I'll try and go into non-mathematical details about basically the processing workflow. And Fred covered mathematics well better than I could, so I'll go more on the practical, what's important and what to care about. All right, so nowadays, thanks to the resolution revolution, we deal with movies. And why do we deal with movies is to basically deblur our images. And so that's really the first step in our workflow. To basically, each micrograph is a set of a number of frames, and you basically align all those frames to each other to get basically a better transmission of the high resolution information. And so that was shown by Yueming Lee in Yifan Chen's group quite a while ago, applied to the TRIP-V1 structure. And you see here, for example, you see two power spectra of a micrograph. And so this on the left is the one without movie alignment. That's what we used to see prior to the revolution. Like some power spectra looked great, some did not, and we didn't really know why actually, what was really going on. But as soon as the movie mode came about, Niko Grigoriev and the Chen group basically showed how things are moving in your micrographs and how this is affecting your resolution. And so here you see no correction basically, and then you have in the center this graph that shows you how basically frame by frame how basically the image is moving in the X and Y plane. And so you can see that the first frames that are at the bottom right, you have a lot of movement, and then it tapers down and it actually changes direction and towards the later frames. And then if you correct for that, you get the power spectrum on the right, which is basically restored. And so you can see that the tone rings of your power spectrum are extending to higher resolutions, as more isotropically. So that's been very important in getting us consistently good micrographs that carry the resolution we need. Now, something that they were also describing, like there's something interesting about this graph. Why is this that we have kind of fast motion at the beginning and then slower motion towards the end of the movie series? And the reason for that is basically that as soon as the electron beam hits your sample, you have a kind of rapid doming of the ice, or the carbon and the ice. And this rapid doming is basically a pretty large movement in the z direction, which you don't really see if your image is flat, but which makes different parts of your image move in X and Y direction as well. So it's like kind of an expansion like this. The reason for that expansion was beautifully described by Chris Russo at the MRC, which is that basically you have a copper grid bars, and you put a thin carbon film on top. And when you freeze your grid, the copper and the carbon don't contract at the same rate and by the same extent. And so basically your copper contracts more than the carbon. And the result of that is that your carbon is wrinkling and loses basically structural integrity after the freezing. And which means that as soon as you start illuminating your sample, it doesn't really have structural integrity, and on top of it doesn't conduct charge very well, and so it charges, and basically it has like many different effects make it basically expand. So that's why gold grids are very important, like those grids that have gold grid bars and gold foil, because they keep their structural integrity when you freeze your grid. So you can correct for all that movement, most of that movement. So in a way, many people have not always seen the difference between gold grids and not gold grids, but it does actually make a difference. And actually, one place where it does make a difference is if you're screening your grid on a TechNice Spirit, which is a very cheap microscope, which does not have movie mode, and you're looking at small proteins. If you have carbon grids, you might not see anything. If you have gold grids, you will actually see your particles. So that's one good reason to start basically looking at screening your samples with those gold Ultra AU foil grids when you don't have movie mode. All right. Something that they were also describing in that initial paper was that if you looked at different regions of your micrograph, actually you could see that basically the graph on the right is basically how things move in those two regions, the black region, the blue region, and the red is the overall. And you see that things are not moving exactly the same way. And so it might be important to look more locally at how things are moving because of this doming effect. And so you want to do a subframe alignment, something that is carried by, I don't remember if it was carried by, I think it might not have been carried by the first motion core algorithm that this paper was describing, but is now carried by the latest version, motion core 2, where you basically make patches. Actually, I have a good picture for that. So you basically make patches across your micrograph, and you basically, after you first do a correction of the whole, like the general movement of the whole micrograph, and then you basically do a sub-correction of each individual patch. And that way you get much more accurate correction of the movement of those different parts of your micrograph. Because you can see, if you look at, these are the traces in each of these patches, and you see that each trace is actually different. And so you need to take that into account to get the sharpest possible images. All right, so that's at the micrograph level. So basically, it's something you can do straight away in your workflow. And the better you do it, the better it is for every successive step. So better use the best algorithm for that. So Motion Core 2 is one of those, which is now works very well. Another one is called WARP, WARP-EM by Dmitry Tegunov, that does basically a very similar approach. CryoSpark now also implemented the same approach. So you can choose between those. Let's say those three, for example, are all pretty much excellent, and you will not find much difference between those three programs. Now, going to one program versus another might have other consequences in your workflow when you do what's called a particle polishing in Refinement, for example. So then it's more practical. There's more practical, let's say, aspects to which one you're going to choose, and maybe we'll have a clear idea about that by the end of this. So the next is actually to not do patches on your micrograph, but actually think about how each particle itself is moving. So per particle alignment, and there is So this patch motion correction is actually almost perfect. So in a way, you might not even need to think about per particle. But it does, like if you're really pushing for that 0.1 angstrom extra that you really want to have, you might want to think about that. So there's two major different ways of doing this. One is called reliant polishing, which is basically aligning your particles in your movie based on a reference. So that's a major thing. It's like later on in your workflow, you reconstruct a 3D volume, you align all your particles to the 3D reference, and you can expand your movies and align basically each particle of the whole movie stack to that reference. Another one is by John Rubinstein in Toronto, also implemented, partially implemented in CryoSPA, where you don't align to a reference, to a 3D reference, you align to the particle itself in the micrograph, assuming that you have enough signal to do that. And it's quite fundamentally, it's important to understand that difference, because if your reference, like in Refinement, you align those subparticles to one single common reference. If that reference is variable, it has heterogeneity, it's not always in the same conformation, your particles will not be so well aligned. Like some of your particles will be well aligned to that single reference, but others might not be. And so your accuracy using this particular method might not be the best. Whereas here, you're aligning, the particle is being aligned by itself, to itself. And so if all your particles are completely like wobbling around in all sorts of ways, this will always be robust. And so you might want to consider using that. Now this, another aspect of this is that I actually forgot to mention it in the previous step, is that this does not re-estimate the contrast loss due to movement of your particles in different frames or due to radiation damage. It has a single model and it applies to that model. Whereas in reliant polishing, you actually re-estimate a kind of a B factor, basically how much contrast loss you have due to radiation damage and particle movement in each frame as you align your particles. And so this is somewhat, if done properly, can be more accurate than the single model good for all. Yeah?
So if you don't have a 3D reference, how does Reliant deal with that? Since when your whole structure is not viable?
If you do not have a 3D reference, so basically this, here I'm kind of describing this before we get to 3D reconstruction, but this is actually done after 3D reconstruction. So you first get, that's not working anymore.
Need more battery.
I might need more battery. Yeah, so this you have to first get your initial reference, do your 3D reconstruction,
Change that.
potentially classify your data, and then you do that. Whereas the Rubinstein algorithm, you can do it straight away. You just need the coordinates of your particles. That's all it asks for. Now you might not want to do it straight away, actually, because initially you may pick, your particle picking algorithm might pick millions of particles, only 1% of which are good, and this is computationally expensive, so better actually clean up your data, get a clean set of particles, and then do that. Oops. No. All right. Yeah, so that's an example from the paper by John Rubinstein, where you can see basically the trace for each particle in your micrograph. And you can see that different places on your micrograph have very different behaviors. So this can really improve the polishing of your particles. And what it does not do, and what Refinement does, is basically assign a B factor, basically a dampening of the high resolution component of the image per frame. And so Refinement will.
Is this cell phone?
So Refinement will basically, actually I don't remember exactly how it does it, but I think it does basically reconstruction per frame. It reconstructs the 3D volume per frame and estimates the resolution of this particular reconstruction, and then assigns a B factor to each of those frames. It used quite a few, it's a probabilistic Bayesian algorithm, so it actually uses as many information as it can to estimate a B factor for each frame, basically, so that it dampens the high resolution of each frame accurately. And so you see that the first frame get a little bit of dampening. That's due to the very fast movement that you have in your initial frames. And then it almost doesn't dampen, let's say at frame 3 to 5, and then it starts dampening the high resolution more and more as you progress because of the radiation damage. Okay, so that's for basically movie alignment, the different ways of aligning movies. Next thing that's extremely important for the end result, for the final resolution that you will get, is basically estimating the contrast transfer function of your micrographs, which is basically mostly estimating the defocus value. So that's the first thing you actually do. It's what makes it vary the most is the defocus value. And so you want to estimate the defocus value of your micrographs as accurately as possible. And so how you do that, basically you see that this is a power spectrum of a micrograph, and you see those ripples, which are basically oscillations in the contrast transfer function. And you see how this is the low resolution of your power spectrum, and you go towards higher resolutions, and you see how they oscillate faster and faster. Okay, and so we can actually estimate the resolution of this micrograph by how far we can see those oscillations, because these oscillations come from basically they are intrinsic to the microscope. They are aberrations mostly coming from the lens of your microscope. And so they are supposed to be there. And so if you don't see them in your micrograph, it means they disappeared. If they disappeared, there's something that went into the way of recovering that information. That information is no longer there. Okay, so you can basically take advantage of those oscillations to figure out, because those oscillations, how spaced they are, basically, depend on the contrast transfer function, and is mostly due to the defocus value. So basically, the defocus value is going to change how much, like how wide those oscillations are. And so you can fit basically a model of the contrast transfer function with different values of your defocus and see which one will fit that data the best. So the way to do it initially is to say, this is fairly symmetric, like rotationally symmetric. So maybe we get more signal if we rotationally average this. And so you get something that looks like this. So the green curve is your data, rotationally averaged, and also background subtracted. And so you see those oscillations and they keep going quite far. That's a good micrograph. And in orange is your model. So that's the contrast transfer function, the mathematical model of it. And this is where this model has the defocus values that best matches your data. And one thing interesting that you can see about this is that you can actually, in a way, you can do the cross correlation between the data and the model and see how far do they agree with each other. And you see that here there's a little dip, so they don't fully agree with each other, and then there's a big dip. They don't agree at all with each other, so maybe we are off by one, we are out of phase. And then the further you go, the less you agree with each other. And so you can, in a way, by that comparison, you can estimate how good your micrograph is, how far you can basically reliably find those oscillations. So it's a good way, basically, that cross correlation is a good way to say, oh, my micrograph here is as good as it can be, like maybe this is going all the way to 2 angstrom resolution. Other micrographs might stop here, and you're going to say, this is not going beyond 6 or 10 angstrom, and maybe I want to get rid of that micrograph. Yeah, so that's a good quality measure. But be careful that as you go further and further away from, like towards the high resolutions, this is oscillating more and more, and you have more and more noise. So in a way, you don't really want to trust that quality measure beyond maybe 3.5 angstroms. Like let's say if it's better than 3.5, probably you can keep, but you don't want to say, oh, this one is 3.4, you might want to get rid of it and only keep whatever goes to 3, let's say, because this is not such a good measure at high resolution. So here it's also actually a good picture to show you why this is important. Because basically the way you correct for the contrast transfer function is by this Wiener filter that Fred was talking about. And a very important portion of that Wiener filter is basically what you're doing is you have your data, or let's say this data, and you have a model of your contrast transfer function, and you're basically, in a sense, multiplying the data by the model function. And the effect of that is that basically those oscillations, here it doesn't show it very well, but these oscillations are positive and then negative and positive and negative and positive. But your actual contrast, the real contrast of your particle, is all positive. You don't have negative electron density. So it's all positive. And so the negative values are not real, they come from aberrations of the microscope. So you want to put them back to being positive. Okay? But and the way to do that is multiplying by the model. If you multiply negative by negative, it becomes positive. And so that's basically how you correct. It's a simple way to see it. Now the problem is that if you do that in that region where it's oscillating very fast, and the model is starting to not agree quite well with the data, now when you multiply one by the other, if they don't agree with each other, if they are not in phase, you get destructive interference. So you're basically destroying your data by correcting for that contrast transfer function. And so that's why you really want that CTF estimation to be as accurate as possible to not destroy your data. Does that make sense? So that's really, really critical in achieving high resolutions. And so one way to have less chance of destroying your data here is actually to collect data at low defocus. If you collect data beyond 2 micron defocus, the oscillations here around 3 angstroms and beyond are extremely rapid, all the way down to less than a pixel, less than a Fourier pixel, so you can't correct for it. But if you go as close as you can to, let's say, 1 micron defocus, then those oscillations are much wider and much easier to correct. And so you'll see that the highest resolution structure there is in the MDB that go to, let's say, 1.5, like below 2 angstrom resolution, they are all collected actually around or even lower than 1 micron defocus. Now there's a problem with that. You get less contrast. So you might want to do that, but you want to be careful. There's a trade-off to have here. But it's also a trade-off to think about also in terms of like if you have a very small protein which has very few features, how you align that protein is very important to your end result. And if all you can use to align your protein is actually alpha helices, you might actually want to have those very low defocus values, or very small defocus values to have as much signal in that 6 to 10 angstrom range where you see alpha helices. Okay, so you might have two advantages of going to low defocus. Okay, so that's one thing. But then, yeah, and this graph actually shows you pretty well what's happening. So let's say if the defocus spread, let's say that if you accurately get a value of defocus for a particular particle, but that accuracy is plus minus 1,000 angstrom. So the best resolution you can get, basically this curve is a dampening of your signal depending on resolution. So if your accuracy is 1,000 angstrom, which is a micron, it's pretty large. No, it's not a micron, it's 0.1 micron. You're losing basically half of your data at 8 angstrom, and you almost have no data left at 5 angstrom. So that's what you get if this is your accuracy. And bear in mind that the ice thickness can be up to 1,000 angstrom. So let's say you have particles at the top of your ice layer and you have particles at the bottom of your ice layer. They have just that's actually the spread, like the inaccuracy of your defocus value for them. And so you're limited to 5 angstrom resolution here. So that's a problem. If you want to go to in the 3 angstrom resolution range, the accuracy in your defocus value that you need is about 250 angstroms. Okay, so very, very narrow. So the defocus. Sorry, streamers. Okay, so as estimating the defocus per micrograph is therefore not enough to get to those resolutions. You want to have a much more localized estimation. So that's something that a program called WARP does very well. A number of programs have been trying to do that. Let's say GCTF has been trying to do that very inaccurately. CTF tilts by the Grigoriev group has been doing that maybe a bit more accurately, but within a single plane. So a fairly simple model of let's say your defocus variations. WARP maybe has been the first one to really do it really well, where you basically measure the defocus across your whole micrograph, and then you fit a model that's kind of a loose model, like a loose model where things can wave around. And so you can see in this particular image how this area is fairly flat, but then things are kind of going sideways on this other side. And this has saved us. This program has saved us when we were tilting data. If you tilt the stage of your micrograph and look at tilted data at let's say 30 or 49 degrees tilted, if you don't have that kind of very accurate model of your CTF values across the micrograph, you will get nowhere.
6 minutes.
6 minutes. This is the most important, so yes, we're good with that. Now, CryoSpark is implementing a fairly similar model now, which is also fairly accurate. So CryoSpark can do that pretty well. CTF Find 4 does not do any of that. So it may give you a good estimate for the whole micrograph, but then you will want to refine that by other ways. Okay, so that's the warp interface. And so in warp, it also does a particle picking at the same time, and so then you can assign basically a single defocus value for each particle that you pick. So each particle will have its own defocus value, so that it's as well as possible, like it's corrected as well as you can. But still, this does not account for the thickness of your ice. So you might want to get even an extra layer of refinement after that. And that's something that Reliant has been implementing lately, basically a per particle CTF estimation that happens basically during your refinement of the angles, of the refinement of the alignment of your particles. Basically, it's at a stage of basically trying to very roughly the idea is that each particle will fit to the reference, will be aligned to the reference more accurately if the CTF is accurate. And so if you vary the CTF, the defocus values a little bit, you'll see that basically your particle will have a peak somewhere where it fits the reference the best. And that's probably its defocus value, the correct one. And Strauss-Reyes has also been developing other higher order aberration corrections that are also very important for very high resolutions. And so these things are implemented in Reliant, has been copied in CryoSpark straight away. But you might want to check if they work better in one versus the other, so watch out with that. It might work better still in Reliant. It will definitely be faster in CryoSpark. So that's basically the utmost, like the best thing you can do to retrieve your highest resolution information. All right, but before you get to that, you actually need first to pick your particles, clean up your data, and get 3D reconstruction. So particle picking has been a big issue in the cryo field for many years. And Fred was just talking about some ways of dealing with it. In a nutshell, the deep learning algorithms are beating everybody and doing this better than it has ever been done. So that's an example by WARP, where you have your original image, and then it can figure out where the crap is in the micrograph, and it can basically fairly accurately tell you where the particles are and where they are not. In contrast, Reliant has a Gaussian blob. So Gaussian blob will not be able to figure out what's a particle, what's not a particle. And even if you use fairly accurate templates, so you do template matching with fairly accurate templates, Reliant will not do that properly either. It will still pick a lot of things in the high contrast region, and Fred was mentioning why that is, because you get fairly high, let's say, matching between, like, let's say the crap in your micrograph has a lot of contrast, and so it will basically give you always a high match, and so, but the deep learning algorithms don't have an issue with that. WARP is not the only one to do that, so Cryolo is also a very good program that uses similar algorithms, and Topaz, developed here, is also a fantastic option. So see with your data which one works the best, but usually this is what we want to use. Okay, and I'll probably finish with particle cleanup, and that's probably where we're going to stop, and we can discuss further after that. you have many ways of cleaning up your pics after they have been beautifully picked by one of those deep learning algorithms. You still have a lot of things that are not what you want. Or there might be damaged particles that don't align well to the reference or whatever may happen. And so you can sort based on statistics of the images. It's moderately efficient. 2D classification, reference-free 2D classification, multi-reference ab initio models, and 3D classifications. So I won't go through statistics. It's not working very well. 2D classification can work, but in many cases, when your sample is not so clean, not so easy to figure out how it looks like and so on, it's not necessarily a good idea to clean up with that. Because let's say here, you're pretty sure about the first 4 classes, but after that, which one is a good class, which one is not, hard to tell. And maybe it's partially good and partially bad. And so sorting out based on 2D classification can be very dangerous because it might remove from your data set those rarer views of your complex that you really need for 3D reconstruction, but that are not present in very high numbers. And so I would tend to stay away from that when you have tricky samples. Instead, you can use ab initio. Let's say in CryoSpark, for example, you can do ab initio model generation, and you can give it several classes. And you run several classes. You tell them that they are supposed to be completely different from each other. That's the setting in CryoSpark. And then you see what happens. And here you see 2 classes look like a clean particle, and maybe those 2 here maybe are just random blobs. And so those random blobs might not be good particles, and the 2 other ones might be the good particles. So you can sort out your data this way. And it might be a lot more accurate than 2D classification. But you have issues with that, because if this does not converge to a good solution, or if you're not sure which solution is good, you might get rid of good people. You might also have, there's an issue with anything 3D, which is that you align, basically, if you look at it in Fourier space, each orientation projection is a slice in your Fourier volume. And so if you might actually accumulate signal in one Fourier slice and not in the others. And so one of those volumes might be good particles in one direction, whereas the other guys are good particles in other directions. So you see you're classifying basically based on direction projections, basically. Projection directions. So you want always to be careful with that. So everything you discard from this, it's not a bad idea to do a 2D classification after that and see if you don't have a shiny class in there for one of those projection directions. Another method that we've been playing around with Oliver Clark is use heterogeneous refinement and basically give it dummy references. So let's say those 2 are my 2 good references I got from ab initio, and then these guys initially were 3B1, the ribosome, whatever else, like a GPCR, things that have different size and shapes. And then any particle that goes to those guys cannot be my guy, because they are all going here, the guys I'm interested in. And so that's actually a pretty powerful way of cleaning up your data set. So you can iterate that a few times, always checking the bad classes with 2D classification, making sure you're not removing things that you shouldn't be removing. And also checking that you're not going too far by doing refinements, seeing what resolution you get. And if you start to get decreasing resolution, maybe that's because you're starting to remove people you shouldn't be removing. Okay. Last slides. One critical thing, so when you do 3D reconstruction, you're aligning your particles to a 3D reference. And you're aligning them, so this is a Euler sphere, so that's basically every possible orientation they can be in. And in Reliant, for example, you start by a global search where you look at every possible orientation, but not in such a fine way. Okay, so you, instead of having that many points, you have, I don't know, 10 times less or 20 times less. Otherwise, it would be computationally too expensive. And then you basically refine having more and more points, but restraining, basically not doing a global search where you look at every possibility, but looking at, let's say, around here. I'm going to try to find my local minimum around here, and so on. And so you want to have enough points to get the highest possible resolution. That's basically the Shannon's theorem that says for a sampling of 8 degrees, you cannot go much better than around 50 angstrom. I think it might be off by a factor of 2, I don't remember. Now, if you want 5 angstrom, you need 30 degrees. If you need 3 angstrom, this is off by about, this is off by a factor of 2, I think. And now, if you want to go, wait a second. Oh, no. Yeah, that's off by a little bit. I think my table, which I published, is partially wrong.
It just depends on the size of
yeah,
the
it's
particle.
absolutely. It very much depends on the size of it. So, yeah, that's something I should mention. The larger your particle, the more you need to be accurate in terms of angular accuracy. Because it's like this. If I'm a rhinanine receptor that's 4 angstrom wide, and I'm inaccurate by just 5 degrees, it's actually 1 hand difference, you see. But if I'm a GPCR and I'm like this, and 5 degrees, it's a sidechain, you see. So it really, this actually depends very much on the size of the particle. But you need to take it into account because this is quite important for the resolution you achieve, but also when you're trying to classify your data. And that's something many people forget about. So many people do classification at a very coarse angular sampling, let's say 15 degrees or 7.5 degrees increments. And add those increments, which are not these ones, which would be, let's say, 1 point every, let's say, 10 degrees along this line. If you're thinking about classification, you're trying to figure out whether your particle should go to class 1 or to class 2, but you're also trying to align it at the same time. It might go to class 2 in one orientation, but then if you tilt it by, let's say, 2 degrees, it actually prefers class 1, you see? And so when you're at coarse angles, it doesn't know which one of the two, and it switches between those two. And you can see that in a Refinement output, it switches between class, 50% of particles are switching between class. And then you go to smaller and smaller increments, 3 degrees, 1, 2 degrees, or less, and particles start switching between classes less and less. That's because now they know exactly where they should be in terms of alignment, and they can really decide which class they belong to. And so if you have minute differences between your classes, that would be absolutely critical in figuring out where to go. So always be careful with that. Check your, if you use Refinement, check how particles are switching class. And if they keep switching, it means you need to go to finer angular increments. All right. Should I stop there? Or?
We'll have to put the slides online, and we
Yeah.
can continue the discussion during the roundtable.
Okay, so I will stop there. But if you want to talk about that, we can talk about it during the roundtable.
We'll talk about it during lunch. Let's thank Amedee. And the short course students, we're going to head back down to the seminar room. We're going to have lunch, and we can talk a lot more about local refinement and other things. Perfect. So we'll see what we'll have for lunch. You can grab lunch.
Sounds good. And there's something to fill off.
Did I just drop drop it down.
Yes. But behind your foot.
Ah, there you go. To minimize the. So head down to the sensory focus room. You can grab lunch first. If you're a speaker, you can cut the lunch. Or you can ignore the lunch.
I should not. It's Max Perrault. He used to always be in line with everybody. You know, he was very busy. He was the director of the institute. And he was like, no.
Before you head out, ask you to either email me a copy of the PDF.
Yep.
Or download it directly.
Was this age appropriate in a way?
I think so. Should be good. So we're going to go downstairs and set up. So we're taking everything out, and we're going to go downstairs.
Particle classes, but that's just saying, these are the.
Downstairs.
Yeah, yeah.
So you can grab lunch.
Yeah, yeah.
So we want to make sure
Yeah, yeah, yeah.
you get lunch first.
Yeah, yeah.